Here's a little magic trick. Say you're running a poll. You're about to call 500 people and ask one yes or no question. You haven't dialed a single number yet, but I can already sketch you the shape of how many will say yes. Not the exact count, the shape of all the counts you might get.
And the wild part is it's always the same shape, a smooth, symmetric bell. Last time we built that bell curve from scratch and learned to read it off one table. Today, we cash it in.
Right. Week 3, Lecture 11, the normal approximation to the binomial. We'll turn those spiky binomial bars into a smooth curve so we can answer, what's the chance, with a single lookup instead of a giant sum.
And then, in the back half, a second big idea that often gets mixed up with the first, the law of large numbers. 2 different theorems, 1 episode. Let's go.
So picture the binomial from a couple of lectures ago, the bar chart for the number of successes. When there are only a handful of trials, it's a few chunky bars. But crank the number of trials up, and look what happens. A binomial count with lots of trials is shaped almost exactly like a normal curve.
Which is great news because the binomial gets painful with big numbers.
Exactly. At least 60 heads out of 100 flips. Strictly, that's summing 41 separate binomial terms by hand. No thanks. Instead, we lay a bell over the bars and read one area off the normal table.
1 area, 1 lookup, done. The giant sum just evaporates.
And on the picture, you can see why it's even allowed. The smooth curve traces right along the tops of the bars. The area under the curve and the total height of the bars are basically the same thing. Let me show you the approximation getting better in real time. 3 pictures, same coin, probability 1/2 each, only the number of flips changes. With just 6 flips, the bars are chunky and lumpy. Think the big blocky pixels of an old 8-bit video game. The bell is in the neighborhood, but it's a loose, jagged fit.
Now jump to 25 flips, then 100. It's like upgrading that 8-bit console to full 4K. The more trials you add, the finer the blocks get, until they pack so tightly the spiky chart melts into a smooth curve. Same dashed bell every time, and the bars hug it tighter and tighter. More trials, closer to the bell, and this smoothing into a bell is a first taste of the central limit theorem, next lecture's headliner.
Okay, let's name it precisely. One bookkeeping note. We'll write little m for the number of trials, just so the letter n stays free for the normal symbol. A binomial count has mean m times p and variance m times p times q. So here's the move. For large M, that count is approximately normal. N of x, MP, root MPQ, same mean, same standard deviation as the binomial.
We're not changing the center or the spread at all. We're just swapping the spiky bars for the smooth curve that shadows them.
One guardrail, though. This is only trustworthy when there are enough trials. Specifically, when m times p is at least 5 and m times q is at least 5.
Both of them, and here's the picture for why. Imagine pitching a wide, symmetric, bell-shaped tent on a campground. 0 successes is a cliff edge on the left. M successes is a brick wall on the right. If p is tiny, the bulk huddles down near 0, and the tent spills off the cliff into impossible negative counts. If p is huge, it smashes into the wall past m. Requiring m times p and m times q to both be at least 5 guarantees 5 units of clearance on each side. So the symmetric tent actually fits inside the campground.
So the headline. Same mean MP, same standard deviation root MPQ, we just switched to the smooth curve. Now there's one subtlety, and it's the single most important thing in this whole lecture, so let me set it up carefully. The binomial count is a whole number, 5, 6, 7. The normal curve is continuous. It lives on every decimal in between. So we have to decide how a smooth curve covers a discrete bar.
And here's a picture I love for it. Think of the counts as floor tiles in a hallway. The tile for 30 has 30 painted in the middle, but the physical tile runs out to the grout lines on either side, from 29.5 to 30.5. The number is just the center. The tile, the bar, is half a unit wide on each side.
Right, so to cover that tile with our smooth curve rug, we don't measure center to center, we measure out to the grout lines. To capture the bar at an integer k, you don't stop at k. You extend the area out to k plus or minus 1/2. That half-unit nudge is called the continuity correction.
And I cannot stress this enough. Forgetting the plus or minus 0.5 is the most common mistake people make on these problems. If your answer's a little off, this is the first thing to check.
So just burn the picture in. The bar for k spans from k minus 1/2 to k plus 1/2. Every problem today is really just, which edge of which bar do I need? Let's make that concrete with the 3 shapes you'll actually use. First, at most x, a left area. You include the bar at x, so you push the boundary up to x plus 1/2, then standardize. P of the count at most x is about P of z at most x plus 0.5 minus MP over root MPQ.
Second, at least x, a right area. Now you're including the bar at x from the other side, so the boundary goes down to x minus 1/2.
And third, between x1 and x2, you widen on both ends, down by 0.5 on the low end, up by 0.5 on the high end.
Here's the one-line rule that keeps the signs straight. Widen the interval by 1/2 on each included end. Narrow it by 1/2 on each excluded end. Include, widen, exclude, narrow. Say it like a mantra.
Let's run one all the way through. A patient recovers from some procedure with probability 0.4. Out of 100 patients, what's the chance that fewer than 30 recover? First, the guardrail. MP is 40, MQ is 60, both comfortably at least 5. We're clear to approximate.
So the center is MP, which is 40, and the standard deviation is the square root of MPQ. That's the square root of 24, about 4.90.
Now the careful part. Back to the floor tiles. Fewer than 30 means the 30 tile is off limits. It's lava. The highest tile we're allowed to stand on is 29, and we walk out to its right-hand grout line, 29.5. Standardize. 29.5 minus 40 over 4.90.
That's a z-score of minus 2.14, and the table gives P of z at most minus 2.14 equals 0.0162, about 1.5%. It'd be quite surprising for recovery to come in that low.
Flip side, literally. A fair coin, 100 flips. What's the chance of at least 60 heads? Guardrail first. MP is 50, MQ is 50, both at least 5. Good.
Center is 50, and the standard deviation is the square root of MPQ, root 25, which is exactly 5. Nice round number.
Now, at least 60. The 60 tile is one we want this time, and we need to cover it from its lower grout line, so we slide down to 59.5. Watch how that's the opposite nudge from the patient problem, where we slid up, include, widen. Standardize. 59.5 minus 50 over 5.
Which is a clean z of 1.9.
And P of z at least 1.9 is 0.0287. So under 3%. 60 heads is a real stretch for a fair coin. And here's a confidence booster. We don't have to approximate. GeoGebra's free probability calculator will give the exact binomial. Pick binomial, set the trials to 100 and p to 1/2, hit the at least button at 60, and it reads 0.0284. Our approximation said 0.0287. Basically dead on. But here's the kicker. Drop the continuity correction, skip that half unit, and the answer slumps to 0.0228, off by a fifth. So that little plus or minus 0.5, that's the thing making the smooth curve actually land on the bars. Worth the fuss. Okay, gear change. Everything so far was about the shape of a count becoming a bell. This next idea is genuinely different, and people blur the two all the time, so let me draw a hard line. The law of large numbers isn't about shape at all. It's about an average settling down. Take a growing pile of independent measurements, all with the same true mean mu, and form the running average, x1 plus x2 and so on, divided by m. As m grows, that running average homes in on mu.
So just to say it plainly, with an image that keeps them apart, the normal approximation is like a long exposure night photo of a busy intersection. One glowing picture of the whole landscape of where every car might go, all the possibilities at once. The law of large numbers is like your average commute time over a whole year. A single number that finally stops fluctuating and settles on the truth. One is a shape, one is a number drifting toward mu. Different claims, different theorems.
And it's a statement about the limit. As m goes to infinity, the average converges to mu.
In plain words, the long-run average outcome equals the expected value. Flip a fair coin enough times, and the fraction of heads creeps toward 1/2. Not because the coin owes you, but just because the average of more and more flips gets pulled toward its center.
This picture is my favorite, and there's an analogy that nails it. Walking an untrained puppy down a straight sidewalk. The puppy is a single random outcome, pure chaos. It darts left to sniff a fire hydrant, lunges right at a squirrel. Watch it for 2 seconds and you'd swear it has no direction at all. That's the running average way over on the left. 2 flips, 3 flips, bouncing wildly. Get 3 heads in a row and you'd think the coin lands heads every time.
But you, holding the leash, are the long-run average, walking a calm, steady line straight down the center of the sidewalk. Over a 2-mile walk, the puppy's average path is exactly yours. March to the right on the graph, hundreds, then thousands of trials, and the wiggles shrink, the line reeled in toward mu and basically locked on. That left-hand chaos is exactly why a tiny sample fools you, the hot streak, the wheel that's due for red, and why enough trials is the whole game. 3 flips tells you almost nothing, 3,000 tells you a lot.
Quick worked one. Here's a game tied to a die roll with a payout for each face. Some you win, some you lose. What's the average payout per game over the long haul? By the law of large numbers, that long-run average is just the expected payout. So add up the 6 payouts and divide by 6. -1, +0, +5, +5, +2, -10. All over 6. That's 1/6.
1/6 of a dollar, about 17 cents per game, in your favor.
And here's the law of large numbers doing its job. Any single roll is the wild puppy. You might step on that -10 landmine, but average over thousands of plays and it heals right onto the calm 17-cent path. The single play is chaos. The long-run average is steady and basically inevitable, which is the whole reason a casino never sweats one lucky winner. Let's tie a bow on it and let the pictures do the recap. Two big ideas today, kept separate. 1. A large binomial is approximately normal. Upgrade the chunky 8-bit bars to a smooth 4K bell. Check your campsite has clearance so the tent doesn't fall off the cliff. That's m times p and m times q, both at least 5. And measure out to the half-unit grout lines. The plus or minus 0.5 continuity correction. 2. The law of large numbers. Trust the calm human on the leash, not the wild puppy. Averages settle onto mu.
And here's the thread into next time. The law of large numbers says an average lands on mu, but a single sample is so much more than just its average. It has spread. It has a whole distribution of its own.
So next up, Lecture 12. Random samples, the statistics we use to summarize them, and the central limit theorem. The grown-up version of that bars become a bell trick we saw today. Now for almost any average. See you there.
See you in Lecture 12.